Okay, in part two of our basic unit on chemistry, we're going to be looking at water and its special properties. It's no secret that water is absolutely essential to life on Earth. And what makes water so important to all forms of life has to do with its polar nature. So recall that the polarity of water molecules comes from the partially negative oxygen atoms and the partially positive hydrogen atoms. This polar nature of water and the hydrogen bonding that occur between adjacent water molecules gives water some very unique properties that are really important to life's processes. So, water is cohesive. And what's meant by this term is that the hydrogen bonding that holds the adjacent water molecules together makes water very cohesive. It sticks to itself. Now, again, we're talking about the hydrogen bonds here. We're not talking about the covalent bonds that actually join an oxygen atom to the two hydrogen atoms to make one water molecule. I want to make a specific statement here that you do not confuse the covalent bonds that form a single water molecule and the hydrogen bonds that are found holding adjacent water molecules together. So, water being cohesive allows for it to stick to other water molecules. And the cohesive nature of water gives water some really unique properties, and we'll look at an example of this in just a moment. Now, water is also adhesive, and what this means is that water will cling to other things. Water likes to cling to other polar things, right? Polar likes polar. So water will cling to other things and it sticks to other things, and you know some examples of this just by looking around at your everyday surroundings. For instance, this is a small insect called a water strider. And the water strider is able to literally walk on the surface of water because of something called surface tension. Now, the surface tension of the water is due to the cohesive attraction of those water molecules forming the surface of the water. And by moving very carefully across the surface of the water strider is actually able to walk across the water. Another good example of the cohesive nature of water has to do with how water moves upwards in a plant. As we'll learn next semester, water is absorbed and taken up from the soil by the roots of the plant, and it enters a special tissue called the xylem tissue as it moves from the roots through the stem and then out into the leaf and then ultimately out into the atmosphere. And if we look at this xylem tissue, it's actually composed of very, very small straw-like the remnants of very small straw-like cells, and the water molecules, as you can see, are held together by these hydrogen bonds. And so as water is pulled out through the stoma of leaves at the top of the plant, it is actually pulling water in a continuous motion all the way up through the plant's tissues. Now, we can also look at a phenomenon called capillary action. Right? Now, capillary action has to do with both the cohesive and adhesive nature of water. Water will also adhere to things like glass. And you know this from the exercise that we did in lab, where you took a drop of water and you stuck two slides together and they stuck together like glue. That was because the water was adhering to the glass. And so in a capillary tube, the water adheres to the glass, but as it's adhering to the glass, it's also pulling up adjacent water molecules, and it can make the water rise up a short distance in the capillary tube. Okay, so a couple of other things related, maybe another example or two related to this concept of cohesion and adhesion. Water will beat up on your windshield. And so in order to get it off and have it move off quickly, you can apply something like Rain-X to your car. Now, Rain-X is a non-polar substance. Water likes polar things. We consider those things to be hydrophilic, but water does not like non-polar things. So the non-polar Rain-X that you apply to your windshield keeps the water from sticking to your windshield, and it allows it to bead and run off a little bit easier. The same thing occurs when you wax your car. You put wax on the surface of your car. That non-polar wax there helps the water molecules to not adhere to the surface of your car, and then it runs off. Okay, so those are a couple of examples of water's cohesive and adhesive properties. We also introduced the terms hydrophilic and hydrophobic there, so be sure you know the definitions of those. Now, water also has a high specific heat value. The hydrogen bonding and polar nature of water allows for water to absorb large quantities of heat and only slightly change its own temperature. Now, if you think about this, water comes in several different states. There's liquid water, there's gaseous water or water vapor, and then there's solid water that's ice. It's all water, but the difference has to do with the energy of the system. As we take energy away and the system cools, so to speak, the water molecules arrange themselves in very predictable fashions, and it forms crystals, these ice crystals. And as heat is added to the system, the ice crystals melt to form liquid water, and as we continue to add heat, the water can turn into water vapor. So what's happening actually is the distance between those adjacent water molecules. The more heat we apply to the system, the faster those things are moving. The faster those things are moving, the more likely they are to move away from one another. And what I'm talking about moving away from one another here are the water molecules themselves. We are basically stretching those hydrogen bonds. The more distance, the more stretched that hydrogen bond is, the less solid the water molecules are when they are formed together. So crystalline ice, liquid water, water vapor, all has to do with these hydrogen and oxygen's interactions forming those hydrogen bonds. Now, water is able to absorb a large quantity of heat. So we can it takes a long time for a pot of water to boil on the stove, right? No matter, even if you've got it on high, because it's absorbing that heat. Once it does heat up, it maintains its temperature for quite a while. Now, this value, known as the specific heat value, gives water some unique properties that can affect our own climate. This is one of the reasons that coastal climates tend to be moderated. Here in Southeast Texas, our climate is very warm and muggy, typically because we kind of live next to the Gulf of Mexico. There's a lot of warmth that comes from that warm body of water. If you go to the western coast around San Diego, the water of the Pacific Ocean is much, much cooler there, and their climate is much, much cooler. Because water can absorb a lot of heat and only slightly change its own temperature. Water is also a good insulator, which is one of the reasons why our cells are filled with water. And as we take water and change its state, as water goes from a liquid to a gas in water vapor, it takes a lot of the energy away with it. And we can look at this phenomenon called evaporative cooling. So as water absorbs energy and changes its state from a liquid to a gas, this heat energy is taken away. So when you exercise and your body is sweating, that water that's put onto the surface of your skin is allowed to evaporate, and it takes that heat away. If you want to increase the rate at which your body can evaporatively cool, you can stand in front of a fan, because the fan blows the water vapor away and helps it to evaporate a little bit easier, and it can cool you down a little bit faster. Water is also less dense as a solid than a liquid. So remember, we talked about those hydrogen bonds and how stable they are when we take away that amount of heat, forming ice. And those crystals are so evenly spaced that ice floats. And you know that from looking at the ice in your iced tea when you drink it. How this relates to ecology is water bodies, as they freeze in the winter, the ice freezes and floats. This insulates the water beneath it. So unless the water body is not very deep, it's very, very, very unlikely that the water body would completely freeze solid. So life is actually able to survive underneath the frozen ice. And in fact, the frozen ice actually provides a good insulator to the water underneath it. As that ice melts, the hydrogen bonds kind of break and are stretched, and our water becomes a liquid again. We can also look at water as the universal solvent. A solvent is a substance that allows a solution to form. Okay, so a solution is the mixing of two or more substances into a homogeneous state. So as an example, if I take a spoonful of sugar, table sugar, and I mix it into a gallon of water, I have now formed a sugar solution. The dissolving agent is the solvent. In my example, that would be the water. And the substance that is dissolved is the solute. In my example, that would be the sugar. If I take a handful of marbles and I dump it into a gallon of water and I mix it around, do I form a solution? No, I make a bunch of wet marbles, right? So not everything will dissolve or mix into water to form a solution. But water does dissolve a lot of things. It is for this reason that it is called the universal solvent. And one of the reasons it dissolves a lot of things is because of water's polar nature. So polar compounds, molecules that have areas of charge like water molecules, or even ionic compounds because of their cations and anions and the positive and negative charge associated with them, are said to be hydrophilic. They are water loving, while substances that do not like water are said to be hydrophobic. And so water does not dissolve these non-polar compounds. And so, for instance, I just mentioned a few minutes ago about Rain-X and the wax that you put on their car. Those are non-polar compounds. So here's an example of how some water molecules may form a solution using this salt crystal as an example. So here's our crystalline salt. It becomes surrounded with the water molecules. The positive sodium ions become attracted to the negative portions of these water molecules, while the negatively charged chlorine ions become attracted to the positively charged, partially positively charged hydrogen ions. This breaking apart of these ionic bonds in this fashion is called dissociation.